Takashi.
My name is Takashi Asada. I'm from FLAB, Nao University. I'm talk about directional dark matter search with ultra.
Use microphone.
Sorry. I'll talk about directional dark matter search with ultrafine grain nuclear emulsion. This is my talk topics. First, I talked about dark matter and our experiments. Then I talk about emulsion R&D. This is my field. And then read out R&D. And finally, I introduce our activity. And then let's go to the dark matter section. And maybe you know well about dark matter, so I introduce very simple. But the left image is in body simulation. It means current universe structure needs cold dark matter, and right image, right up top image is result of the Planck, and it means ordinary dark matter has 5 times bigger than ordinary dark matter. And right bottom one is galaxy rotation curve, and it is indicates the dark matter exists very local scale. Then this is our Milky Way galaxy rotation curve. And recent results shows that our solar system is has a rotation velocity of the 240 kilometers per second. And it means that from this result, we can calculate the local dark matter density near the solar system. It becomes 0.3 to 0.5 GeV per centimeter cubic. And if we suppose the dark matter mass, we can calculate the flux of dark matter. And the distribution of velocity of dark matter is also suppose that the maximum speed is limited by the escape speed of the galaxy, and the distribution is almost suppose the Maxwellian. This is a one of the theoretical type, and also some other theory exist, but Maxwellian is the most simple solution. And there is some experiment to detect the dark matter. They detect dark matter as a WIMP, which means weakly interacting massive particles. And such experiment is called the direct dark matter search. They use some methods to detect them, but their result is already described as the energy specters. Their scheme is that the dark matter solar system is moving inside of the dark matter air, and the dark it means that the solar system is received the WIMP wind, and also Earth is revoluted, so the WIMP wind speed is oscillating according to the Earth's revolution. So their experiment can detect the annual modulation. Some experiments already say that they found the annual modulation. The right upper one figure shows that the Dama regular result. It is very clear annual modulation is observed. And also other experiment called Cogento is said that they found annular modulation, which is consistent to the modulation of the Dama and rotation of the Earth. But some other experiments like CDMS and Xenon say that their cross-section region is already excluded. So the discovery of the dark matter is not concluded yet. And then we try to discover the dark matter existence from the other aspects. The scheme is that the WIMP is come from the same direction because solar system is moving to same direction. It comes from the signals, and because of the Earth is rotating, the direction is changing. But if we fix to the detector to the WIMP direction, we can integrate the recoiled signals from the same direction WIMP wind. So if it is possible, we can calculate the WIMP wind direction. So it means the other proof of the existence of the dark matter. The directional dark matter search is some experiments do this directional dark matter search, but all other directional dark matter search is use gaseous detector. Gas detector can extend the flight length of nuclear recoils, but they have a problem of the diffusion. They detect the signals as drifted electrons, so it becomes a problem of size limit. But nuclear emulsion can limit the diffusion inside of their crystals. So diffusion problem are nothing. If extreme short flux is detectable, large mass experiment is relatively easy. Of course, you know the very large mass experiment like opera, so large mass experiment is already proved. And this is expected range of the inside of the emulsion. And you can see that all of the flight length is less than 1 micron. So we have to detect several 100 nanometer tracks, and it needs very high resolution emulsion. And this is a simulation of the if we suppose the certain range threshold. If we suppose the 100 nanometer range threshold and 25 kilogram per year mass experiment, and we can cover the Dama region. This is very ideal suppose, but if we achieve this range threshold, we can cover the Dama regions. And then I'll introduce how realize such experiments. To detect such very short flux, the crystal size is very important. Like opera type and some other more bigger crystals cannot detect such short flux because the recoiled atoms cannot make tracks. But if we keep high crystal density and make crystal size micronized, we can detect the atoms as a track. So micronization is the key to detect such short tracks. This is an introduction of our facility in Nagoya. We introduced the emulsion production machine from the 2010 year, and the machine can produce one batch per 4 hours, and the scale is 100 grams per batch. It is enough to our lab level study, and thanks to the machine and cooperation of Fujifilm office, we can do very flexible study. And this machine can produce many kind of crystals, like for opera type for MIP grain crystals, and such very fine crystal is used for our experiment. And we planning a new machine of the triplet volume. And this machine can produce 20 kilograms per month, so we can do about 100 kilogram scale experiment. So we can do such a 25 kilogram experiment to cover Dama region with this new machine. Of course, the micronization is very difficult, but I found the new method to produce fine grains. The problem is flocculate. If the initial crystals become very fine grain, but some process during the production, like washing, sensitizing, makes the crystals flocculated. It causes like this picture, very not cubic and not cyclic and bigger crystal. But with new method using polymer, polymer strongly covers the crystal surface and disturbs their flocculate. You can see the light two picture. This is comparison of the two methods. The same color line means that same recipe, but only bottom one use polymer new method. So you can see that new method can produce very stable crystals.
You put polymer during sensitizing process? Exactly polymer.
Just we add polymer at the initial because just after the next steps can flocculate the crystals before the sensitizing.
You put polymer before sensitizing, then it's okay?
You afraid the sensitivity?
No.
Hmm?
Oh. What is the difference?
Complete same recipe, but only the bottom one adds the polymer. The recipe, the construction is same. Later, I explain. Thanks to this new method, we can produce the very fine grain. The left image is opera type emulsion, and it has 200 nanometer crystals. And the zooming image is the same zooming length to light 2 image, and you can find that the both two is very micronized. Upper one is now current R&D type, and bottom one is our best fine grain type. This is post to a batch of the size distribution of the batch. And this left one is called NIT, is current R&D, main R&D type, and it is used for test run. And right one is called Ultra NIT, is most fine emulsion, which main size is 18 nanometer, is used for more future physics run. their reproducibility is very good, and the size is stable, while the density is 3.0 to 3.7 gram per centimeter cubic. The important things is that how the crystal is crowded. The left NIT type has 12 crystals per micrometer, and if ultra NIT type has 13 crystals per micrometer. It means that they can detect 200 nanometer or less than 100 nanometer tracks. According with the carbon tracks, the tracking energy threshold becomes NIT type becomes less than 80 kb, and ultra NIT type becomes 35 kb. This is incredible value, but this is only theoretical value because the sensitivity is not included. This is image of the implanted ions. Right picture is image of the krypton ions, and it can detect well krypton as a tracks. But krypton has a high energy deposit, but carbon is relatively low energy deposit. So the tracking efficiency of the NIT is this is preliminary result, but 50 nanometer carbon tracks is detected by the 80%. And 80 kilovolt, it becomes 250 nanometer tracks is detected only 50%. I calculated that each crystal sensitivity from these results, and it becomes 50%. And also, ultra NIT type has very small, so the path of the particle becomes more shorter, so the sensitivity becomes quite low. So our next task is sensitizing.
What is the charge state of krypton?
Charge?
Charge of design. Charge, ionization, degree of ionization of krypton. Krypton +1, +2?
Upper one is +1 and bottom one is +2, because the facility is only to accelerate 200 kilovolt. And this is only plan, but we plan to control sensitivity. The sensitivity control is not so simple because there are backgrounds. Main background is come from the intrinsic radioisotope, and it generates the electron background. But electron energy deposit is almost lower than 10 kb per micrometer, and our target, carbon, nitrogen, oxygen, is upper than 100 kb per micron. So if we can make the threshold between them, we can only detect signals but reject backgrounds. To detect, make such high contrast threshold, we now studying following sensitizing method, like doping impurities to capture electron and electron holes, and adding pigments or chemicals on surface to sensitizing or antifog. And also developing is studied for sensitivity control, and also the more fine developed grains to improve the resolution. Okay. Then let's go to the readout R&D. The concept is that we use the high-speed optical microscope for candidate selection and more high-resolution microscope to signal confirmation. These two combines our concept. I introduce this readout procedure with a certain test case. First, let's go to the optical microscope section. This is the real optical image of the nuclear recoils from the 14 MeV neutrons. And this is almost recoil of bromons because we tuning very low sensitivity tuning at that case, but almost this is system is almost same to our realistic experiment. And first, you can we take a picture all of the volume and fit the bright grains to ellipse. You can see that the grains like it's not circle but ellipse. So we can choose that signals from backgrounds by that ellipticity. Then to reject the defocus layer, we do the best focus selection. And all of these processes is completely automatically done, and we can finally get the information of the ellipticity and 3D position and brightness, shape, and area and angle and many informations. And then candidate is selected. We move to more high resolution confirmation. This is an introduction of the X-ray microscope. X-ray microscope is constructed inside of the Springwaite in Japan. This Springwaite is the world's largest synchrotron radiation facility, and we use the 8 kb X-ray. You can find the this picture is 17 nanometer lines and 17 nanometer space, and you can find each lines. Theoretical resolution is calculated as 62 nanometer. And you can see that this optical image is becomes very clear tracks in the X-ray image. And the matching efficiency is almost perfect, and the shift from prediction position is enough short. So the matching is no problem, and we can detect confirm the signals and backgrounds with this process. And this is the check of the efficiency of the optical selection. First, we take this is the picture of the ellipticity inside with the optical image, and this is a minor shorter band, and the vertical axis is the measure parameter. And if we add the X-ray microscope information, we can reject the noise. This is almost constructed from single grain, but with the optical image, it becomes a little ellipse-like. And with this information, we can draw a cut line between these two. And these signals indicate that red signals indicate that incidence direction of neutron, like this picture. And the bottom picture is optical readout efficiency with this black cut line. With this cut line, we can detect more than 200 nanometer tracks by only using optical microscope. And more detailed confirmation is done by X-ray microscope. Like this process, fundamental readout system is already established. And this is a study for upgrade. Now the scanning speed is 0.1 gram per day. This is enough for test run, but not enough to physics run. So we have to upgrade this scanning speed. And we plan to upgrade the optics. We change objective length and wavelength, and it make the ellipse shape to dull ellipse to sharp ellipse. And also plasmon analysis is studied, and it because of the developed grain is very small crystals, so plasmon effect is happened. It including the crystal size information, and also it depends on the energy deposit. And finally, fluorescence study is very hopeful study. Fluorescence gives us the super resolution around 50 nanometer. If it becomes possible, we can detect signals and confirm signals only optics. Finally, I introduce our activity. This is our near future plan, and now we studied about in laboratory state and sensitivity control and new data method. But then next year we plan to 1 gram scale test run, and for this test run we have to understand background. And within several years, we plan to do 10 gram to 100 gram scale physics run, and it needs more high sensitivity, routinity, and equatorial telescope facility, and more high speed system. And finally, we want to reach the kilogram scale for dark matter for Dama region. This is the introduction of our facility in the Grand Sasso. Maybe some people know that facility, but in Grand Sasso, there are already space for immersion pouring and developing. And also, we plan to test run inside of the facility, and maybe physics run is carried out inside of here or near here. And there is near the here some dark matter experiment exists, so this position become a good reference for them. And this is our collaborator, mainly in Nagoya University, but some European people collaborate with us to simulation and optical stage construction. And this Chiba University and Fujifilm researcher collaborate with us. They are specialists of the photographic films and immersion producing. And some spring-wet people collaborated with me for X-ray microscope. And finally, I introduce to you that our cooperation meeting. The first dark matter meeting, sorry, I forget to write the date, but this is 2 months ago. First dark matter collaboration meeting is held. Participants is Nagoya, Napoli, LNGS, Padova, Dubna, Moscow, and the topic is following things. And also, second meeting will be held on the next month. So if you become interested in our experiment, let's join the meeting. This is summary of today's talk. Thank you for your listening.
Thank you very much. Question?
comment on some peculiarities of development of this emulsion, how to hold these sizes, but just cover more on development. Is it some more specific than
developing our
development, chemical development?
yes. The to improve developing, of course, the sensitivity is important, but more fine-grained developing crystals is also important. So we now try to develop with not silver, but use gold. Gold developing. It can very fine small grains, and also for X-ray microscope, it is high density, so it can get more high contrast. So some useful character. That developing method has some good future, but sensitivity is not only depend on the developing, so it is collaborated to the crystal and developing. So first we have to develop the resolution.
You have a question?
Yes, but
Okay.
I have no doubt the Amazon can work for tracking of the planet and meter. How about background, intrinsic background? How much you can reach in sensitivity?
Yes, it is not yet now studying, but main is more carbon, and now maybe very much background to detect gamma region. So for final physics run, we have to reject the gelatin, the carbon 14 inside of gelatin.
How
So
about
for the exact value is not calculated yet.
this you can estimate even without any physics run, any background test?
It is now processing. Maybe a background study is finished. Background estimation is finished maybe this year or next year.
Very short question. Could you explain briefly about the fluorescence?
Fluorescence? Yes. Fluorescence is two sorry, a little too dark. This is only the laser image, and fluorescence image is this one, but it is more clear one, but maybe you can't hear. Yeah, you can. The process is that make incident the laser and get the fluorescence, but some bandwise add some bandwise other laser, and it deduct the bandwise of signal laser. Sorry. First, signal light is like here, and if we add the bandwise laser, it detects the band of the signals with the exciting, de-exciting of the signal luminescence.
Is this completely new method?
Not, it is used for some other medical application, but it is not used for emulsion, nuclear emulsion. So the problem is how to add the luminescence to the crystals.
May I ask you, all your report connected with searching cold dark matter. What about theory prediction? No hot dark matter, only cold?
Yes, hot dark matter is difficult to detect with our detector. Yes. Some believe that previous experiments they reject the more light dark matter. So the most expected region is here, and more higher region is also rejected, and light region is also rejected. So this relative light region is most expected.
We hope. Thank you. And also question connected with slide 20.
20.
When you demonstrate, what is this one? Previous.
Yes.
Previous. This one.
Okay.
How you receive this photo in electronic microscope? What about emulsion? Emulsion was development before or no?
Yeah, development. And it is this emulsion don't have the protection coat, and directly implanted the ions and develop the grains, and electron microscope can observe the reflection of the electrons. So only surface we can observe the signals. Reflecting, scanning electron microscope, electron reflecting.
Well, also, as I know, when you work with electron microscope, you should have high density tracks, because very difficult to search in large field of view. What about this one? How many tracks per square?
Tracks? You mean that?
How many times is necessary
yes.
to search one track?
It is depend on the zooming rate, but the most problem is that electron microscope needs cut the samples, and very small samples is only used. So maybe the speed is not becomes, but scanning electron microscope is very low speed, and transparent electron microscope is relatively high speed, and maybe transparent electron microscope is not have not problem of the speed, but it is very destructive observing, so it cannot use for other experiment.
Okay, thank you very much. Well, if no more questions, thank you very much again. Well, then our next speaker. Morishima Fukuda, development of fast and photon detector in high gamma ray.
Yes. We got it. Okay. USB がない。あ、Okay. I'll talk about the development of fast neutron and
May I ask you, use microphone?
Okay. I'll talk about development of fast neutron and proton detector in high gamma ray background, high gamma ray fields and its application. Okay. This.
Maybe it's better to only this computer and not
Yes. USB.
you give us the presentation and
Professor Takashi, may I ask you, you told, now we have some interaction, you told about next meeting in November. Do you know complete date and place? Ransasa, date? Approximately middle of November.
USB. First, no, no, sorry. Yes. I talk about the development of fast neutron and proton detector. Okay. This is my talk. This is contents of my talk. So I will talk about this is proton and neutron tracks in nuclear immersion, and I will talk about application in normal condition, and I will talk about application in high gamma ray fields. So high gamma ray fields made from high density plasma measurement and or high laser experiment, high power laser experiment. So we are studying the sensitivity control method of nuclear immersion in order to apply nuclear immersion to this field. So I will show you this. This table shows our application, ongoing applications. So I will show you first. I will show you this proton and neutron measurement and radiography. So we have conducted the proton beam measurement at high Mach and high Mach at NIRS in Japanese Hadron Therapy Center. So this picture shows the experimental setup, and this yellow line shows the proton beam line, and this is nuclear immersion. Nuclear immersion is exposed to proton exposed to nuclear immersion in vertical direction. So this is proton tracks, and this is immersion structure. And in this experiment, about 156 MeV proton exposed. And this yellow part is immersion layer, and the blue part is plastic supporting layer. And in my talk, we use opera film and our Japanese scanning system track selector. And the principle of this system is taking tomographic images in the nuclear immersion and reconstruct these tracks by using these images. So, this system read out the track position and angular to grain density, and this system and new and developing new system are presented by Yoshimoto talk today. And this shows reconstructed tracks by our systems. So this direction, X direction, is the incoming proton direction. And this is close-up view, and this yellow line shows the tracks found in one immersion layer. And this is one plate, and this is one plate, and this is so. This track is reconstructed passing through some plates, and you can see the straight proton tracks are reconstructed in our system. And this measurement accuracy is shown in this figure. So position resolution is less than 1 micron, and angular resolution is a few milliradian. So this is a very good resolution, and the detection efficiency is over 99% in one immersion layer. So this performance is enough for immersion analysis. And then, next, we are trying to proton radiography with Korean college at National Cancer Center in Korea. And this is a setup view of the proton radiography. So this shows this gray part shows the aluminum stopper, and this is immersion. And in this experiment, we exposed 30 MeV proton in vertical to the emulsion. And this red line length shows the range of proton expected. So this is a scanning result of the proton tracks reconstructed in our system, by our system. And this is a histogram, cross-sectional histogram of the track length. And this is the same picture. So we have detected the proton absorption image in aluminum with nuclear emulsion. And we are trying to fast neutron detection with nuclear emulsion. So this is the principle of detection of fast neutron with nuclear emulsion. So the fast neutron scatter protons. So we can detect the proton tracks in nuclear emulsion. So parallel neutron beam exposed to the nuclear emulsion, we can get these track image in the emulsion detector. So not parallel tracks. These tracks are scatteringly featured. And we have conducted test DT neutron measurement experiment at 40 MeV neutron facility, AISC. This institute is Japanese standard. This is Japanese institute. And this is emulsion detector, and this is the tritium target, and deuterium beam exposed to the tritium target, and then DT interaction was happened in this area. So we can detect the 40 MeV neutron by using nuclear emulsion. So this is in this experiment we irradiated 10 to 7 neutrons per square centimeter. So this is the result of the reconstructed image of reconstructed image. So neutron, 40 MeV neutron coming from this direction, and these tracks are scattered protons. So looks like this. And this is a close-up and from different angle picture. So you can see the proton tracks scattered in the emulsion materials, and very short tracks. So this is a comparison between proton and neutron tracks. So this is 50. This is high energy proton tracks, and this is low energy neutron tracks. So it is possible to separate between these proton tracks and neutron tracks by using these features. For example, straight or scattered or penetrating tracks or generation and stopped in nuclear emulsion. So by using these data, we are discussing about medical application with hadron therapies. And next, we are conducting the DT neutron measurement at FNS, fusion neutron source, at JAEA in Japan. So this is a collimator beamline. So the DT neutron source is at the back of this collimator. So the collimator beam spread like this picture. So we have we use 4 emulsion detector. 4 emulsion detector placed here and here and here and here. So this distance is the same distance, about 2 meters. And we have tried to the imaging of this neutron beam shape. So this is the result. This is the neutron tracks 2-dimensional position distribution. So we have detected clearly this collimator shape. And this is 4 meter position, and 6 and 8 meter position. So we can detect the clearly spread shape. So we have validated the first neutron imaging with high resolution in this experiment. And now we are planning to apply to first neutron imaging for non-descriptive inspection for large structure, concrete structure. So this target of this target of this measurement is detection of the gap of this is concrete bridge. So we want to know the gap of concrete and breaking of thickness of steel line in this large structure, concrete structure. So we are discussing with RIKEN people. This neutron source is accelerator first neutron, and this accelerator was mounted on the tracks, and this system is mainly position. This system measures out of positions. So this is we are planning to the test experiment setup. So we are planning to conduct test experiment next month in RIKEN. And next, I show you about application in high energy gamma ray fields. Nuclear fusion plasma diagnostics is very important for understanding the plasma fusion mechanism. So we are trying to detect DT or DD neutron in very high gamma ray background. So this is a cross-sectional view of the fusion reactor. This picture is ITER, and DD or DT plasma was confined by this magnetic field in order to keep high plasma density for fusion ignition. So, but gamma ray was generated in plasma and passed through this material. So the measurement condition of the neutron is under very high gamma ray background. So we are developing yes. So we have conducted a test experiment at KSTAR. KSTAR is a Korean fusion reactor. So this is a picture of the reactor, and this is a top view of the reactor, and this purple field, purple region is plasma distribution, and this is structure of the reactor. And we have placed the nuclear emulsion in this position and measured and try to measure the neutron. But this is a developed film. So very, you can see the very blackness. So in this emulsion, there are a lot of electron tracks results from many gamma rays. So we cannot analyze this emulsion. So we need to control sensitivity in order to discriminate gamma rays, in order to analyze this film. So we are developing a sensitivity control study. So this figure shows the energy deposition, DDX distribution of each particles. So this blue line shows the gamma ray, and this green line proton, and red line is alpha. So our standard threshold of the sensitivity is this line, but this is too high sensitivity for the plasma diagnostics. So we try to control this sensitivity from this line to this line. This line can detect a proton, but not sensitive to gamma rays. So we are trying two methods like this. So one method is desensitizing developer, using desensitizing developer and making desensitizing HBr crystal by our emulsion gel production system. So this is the result of the sensitivity control. So this is normal emulsion. This is opera film. This is opera film. So you can see the proton track. These emulsion was exposed by californium, neutron, and gamma rays. So you can see the proton. It is difficult. It is impossible to detect the proton tracks because there are a lot of gamma ray electron tracks. But this is the normal emulsion was developed by desensitizing developer. So you can see clearly proton tracks, and a lot of electron tracks were rejected. And this is unsensitizing emulsion was produced by our production machine. So we can see this picture. You can see very clearly proton tracks. And this picture shows unsensitizing emulsion and was developed by desensitizing developer. So this is the best choice in for parameters. So we have achieved the good emulsion detector. And this emulsion is able to be used in 10 to 8 square centimeter gamma ray field by another checks. So, no, not this condition. This condition is maybe 10 to 5 or 10 to 6. And this is this is the normal development result, but we have tried to develop the sensitized development of this another films, so we can analyze this emulsion. So, and by using this method, we are trying to try new neutron distribution. New neutron imaging method. We are trying. So this is a collimator, a pinhole collimator, and this is emulsion. So this setup is shown in this figure, and this system named neutron pinhole camera. So because the principle is same as light pinhole camera. So this pinhole collimator was made of tungsten, and this is the plasma DT plasma distribution. So if here is a high dense region, so this neutron was produced in this region. So neutron exposed to this area. So we will detect the neutron position distribution like this. So this position. So by analyzing the analysis, by analyzing this distribution, we know where come from the neutron. So this neutron camera was placed in here, and this is the preliminary result of this neutron camera. So this shows the position distribution of detected neutron tracks, and this white cross point is the vertical direction of this detector. But in this, you can see the neutron high neutron track density position is not same this cross point. So by using this information, we can know where come from neutron. So for example, this direction is this direction. And also we can measure the track length by using microscope. So we can measure the neutron energy by using this data. So this is very preliminary data. This axis is neutron energy, and this axis is count. And another application was conducted. We have conducted the fusion plasma measurement at NSTX, Princeton University in USA. So this is a side view of the plasma density. So this white color is high density and red color is low density. And this is in this experiment we use polystyrene and red collimator as shown in this picture. And we use a very small emulsion detector. This detector installed in these three collimators. And we have analyzed these emulsions, and this is the result. And this axis is detected Grigor proton tracks, the number of proton tracks, and this direction is position, each position. So this position is this direction, and this position is this direction, and this is this. So we have achieved the consistent result of expected plasma density. So this result is the first result of plasma neutron density by using nuclear emulsion. And now we are proposing nuclear emulsion method as new DT neutron measurement technology with NIFS. NIFS is National Institution for Fusion Science in Japan. So we are proposing to ITER. So this is ITER. This is the candidate placement of the nuclear emulsion detector. And this position total neutron flux is about 10 to 9 square centimeter per second. So it is enough flux for the emulsion measurement. So we can measure the neutron spectroscopy and imaging in this placement. And I will show you another application. So laser experiment. So now we are trying to nuclear emulsion technology to laser acceleration measurement. High power laser experiment. So this shows the laser fusion reactor. So laser fusion reactor needs very high power laser. Needs very high power laser. So Osaka University have very high two lasers, LFX and Gecko laser. So this is the center part of the fusion point. So this laser is concentrated into this position, and this position is this deuterium doped material is installed here, and then another laser exposed to this material. So you can see this figure. Please see this figure. So this compression part is this part, and the ignition part is this part, and then DD reaction was occurred, and a lot of neutrons are produced in this reaction. But by using very high intensity laser, so the estimation of the number of estimation gamma ray background is 10 to 13 gamma rays per laser shot. So we are trying to do this measurement in next month. So this is a nuclear emulsion detector. So we will use unsensitizing emulsion and desensitizing developer method. So this nuclear emulsion will be installed in this hole in order to close to the burning point. So this we will try to do this experiment. And another application, a final application is this application. So laser acceleration at JAEA. So this is hyper laser, using hyper laser. So this laser was concentrated into very small area, and this area was filled with target gas. Target gas was made of these materials. So these hyper laser generate this photon pressure accelerates these ions. So some ions accelerated by this mechanism. So, but this mechanism is not clearly understood enough. So we need to measure the accelerated ions energy and direction and so on. So we will try to use the emulsion detector. And in this field, our expectation of the gamma ray background is 10 to 9 gamma ray per square centimeter. So this exposure was already done October 2002, October in this year. So this is the preliminary result. This is normal development of the emulsion, and this is desensitized emulsion, the development of the emulsion. So we cannot analyze in this condition, but we can analyze this condition already checked. So we will scan and analyze soon. So that's all. This is conclusion. We are developing a proton neutron detector and start applying this technology to many fields with many institutions. And sensitivity control is very important in high gamma ray fields. And we are developing this technology and apply it to fusion plasma diagnostics. And also we are planning to apply this technology to more heavy particle detection applications. So for example, like this. And this is a more desensitizing crystal test. So this is neutron tracks is not sensitive, but alpha tracks is sensitive. So we are trying to more heavy particle. That's all.
Can you show previous slide? My question is that if you want to see acceleration of ions, to see actually ions, the problem is not that accompanying gamma also, but also you can have visible light from this laser. How you protect against visible light, visible component of light of laser?
We are using magnet.
You separate ions. You make separation of ions, yes?
No, separate electron tracks.
Separated. But visible light, there can be visible light of laser.
Visible light. Visible light. Visible light is so emulsion is coated, aluminium.
Covered. But ion can energy. What is energy of accelerated ion? In this case, MEV. How it penetrate through light protector?
Not penetrated.
Not penetrate.
Yes.
But how do you detect it?
Hmm?
Accelerated ion.
Ионы проникают свободно в легкий алюминиевый пакет, а свет не пройдет и не прозрачный.
But energy of ion in this laser plasma is not very high.
Пакет непрозрачный.
It's not about envelope. It's about energy. Energy of ion, I will believe, about 1 MeV per nucleon, and ranges in material of the order of microns. So, what is the thickness of your light protector?
Okay. Sorry, may I ask you, you demonstrate possibility of using your detector to check concrete construction. You talked about neutron source and detector. Why neutron source? Question, what about radiation safety? And question, why neutron source better than muon?
Sorry, your question is
No, before.
before
What's this one?
this one. Okay. This one. Sorry. I don't understand.
What about radiation
Safety. Yes. I don't understand the detail enough. But not so high intensity.
Okay. Why neutron source better than cosmic ray muon for such task?
Okay. I'm discussing with Riken people. We will try to neutron and muon radiography.
And you compare.
We, we are starting discussing about
only stuff.
yes.
Thanks.
Yes.
No more question?
So question. Now you have many applications. So how many people are involved in this application?
How many people? Me and yes. Many institutions. We our collaborator.
Yeah, but from emulsion side.
Emulsion side is very a few people. Me and almost all my study.
Very effective work. Okay.
How much energy for this?
This energy is broad energy is broadened from 1 MeV to 10 MeV. From 1 to 10 MeV.
This picture is, of course, not clear.
Yes.
Yes, so okay.
And when it will be available, realized?
This experiment.
No.
This is I don't know detail, but maybe a few years ago. Next a few years.
For neutron measurement, you already established the tracking
Not yet tracking.
scanning system.
Not yet tracking. For example, we cannot we cannot measure the track length. But in now Yoshimoto is thinking about the method.
And for this, do you need a scanning speed?
In now not so high speed. No, not needed.
Okay. Thank you very much again. Well, next speaker, Dr. Fukuda Tsutomu. Automated
これはだからつけとけばいいだけだ。
nuclear emulsion emulsions using new tracking technique.
Good morning, everyone. I talk about automated analysis of nuclear emulsions using new tracking technique as presented by my name is Fukuda from Toho University. First of all, I introduce the history of automated analysis of nuclear emulsion in Japan. The modern application of nuclear emulsion in the field of high energy physics has been progressed with the development of automated track recognition technology. In 1970s, the NIWA designed an automated tracking algorithm. Then the Aoki and Nakano and many other people developed practical and high-speed systems. So we call the track selector TS. And these systems were applied for Fermi-level E653 experiment and the Chorus, Donuts, and also Opera experiment in success. This is the time, and this is scanning speed. And the next generation high-speed system, the Hyper-TS, today the Yoshimoto's talk. Okay, so this is the introduction for my talk. Nowadays, the technique of a high-speed emulsion scanning system has made a major progress. But on the other hand, new development which is qualitatively different from conventional strategy, the speed up, is almost also important to open up new possibility for the future. And then we have been developing the automatic track recognition technique of nuclear emulsion on basis of new concept, the large angle tracking and high discriminating tracking. In this talk, I focused the tracking technique. I will introduce pioneer works of developing such a new tracking technique, and its application for scientific analysis. Okay, this is we call the fine track selector FTS at Toho University. This is system overview. The important point is 2 points. One is the large view size. This is enough size for large angle track within one view. And also this is the GPU applied. So in this system, we applied for the tracking at GPU. This is a good flexibility to improve tracking algorithm. Okay, so start large angle tracking. For large angle tracking, I applied the conventional tracking algorithm. This is the Opera film. The emulsion layer on both sides of the plastic case. And we take 16 tomographic image. After that, we image processing, the smoothing and binarization, and hit expansion. After that, we make the coincidence of 60 tomographic image. Okay, so after that, we get the track coincidence, and in this case, the 10 hit number of hit is 10, so the pulse height is 10, and in same time we get the angle information. Finally, we make the threshold of pulse height, so we recognize the track. So this is the raw image, and this is the recognized track. Okay, so this is one view processing. After then, we scanned the first down and next upstream, and also move next layer, and scan the downstream, and upstream. So this is a spiral scan. And this is a scanning result, the 5 millimeter times 3.5 millimeter. So this is the track view. So this length showed the tangent theta 2. So you can see the many large angle track. Okay, so I explain the physics motivation with the large angle scan. The hadron interaction analysis is very important for the verification of Monte Carlo to estimate tau 2 hadron decay channel background in the opera experiment. And also, we also wanted to reduce this background. So this is our signal, the new tau interaction and the tau decay. This is a background, new mu NC interaction, and the hadron the interact immediately. This case is a background. But the nuclear fragment from the vertex is a very strong proof of hadron interaction because signal is decay. So, but nuclear fragments are produced in the nuclear evaporation process caused by the excitation of a nucleus, and they are emitted almost isotropically. So sometimes, almost time, black track is out of acceptance. So the scanning system with wide angle acceptance is required for the systematic nuclear fragment search in hadron interaction analysis. We have been studied hadron interaction in the opera type ECC. This is the result. So the reconstructed result and the hadron beam. So 10 ZeV and 4 ZeV and 2 ZeV. So this is the scan by at normal angle acceptance, tangent theta less than 0.6. This is each momentum multiplicity and king angle for one prong event. So this is data and Monte Carlo. Data and Monte Carlo is a good agreement. Then we search for black track. And this is scanning area and the angle acceptance tangent theta less than 3.0 and the impact parameter for the vertex. And the estimated number of background is negligible. After selecting candidate, I checked confirmation. So this is each angle parasite distribution. So we detect the large angle black track. And this is the analysis result for nuclear fragments in hadron interaction. This is the associated probability of a nuclear fragment, so each momentum. And the topological aspect of nuclear fragment, the multiplicity, and the slope distribution. So also this is data and Monte Carlo. Data and Monte Carlo is a good agreement. So this result allowed to reduce about 30% hadron background in opera. Okay, and also we found the tracking efficiency of large angle MIP is kept sufficiently high in large angle black track analysis. So this is a parasite distribution on both side track. The parasite distribution of large angle MIPS also make this mountain. So green is the large angle MIP. So in the opera film, the MIP at the grain density is about 34. So we want to confirm this result. We try to have a beam exposure at Salon to make a sample for evaluation of a large angle scan. So this is our sample, 12 opera film, and we expose the beam and other angle. This is the exposed beam angle distribution. Okay, and this is the analysis and results of automated scanning of large angle MIP. In this time, we investigate this angle for allow the lead. And 5 film is scanned and connect, and we check middle plate the sense or for the calculated the efficiency. This is the result of efficiency. Horizontal value is the tangent theta. This line is tangent theta 1. The normal acceptance of previous scanning system, and you can see the high efficiency for large angle MIP is confirmed by test experiment. Also, this is a parasite distribution of each angle. Okay, I have a short summary. We developed a technique for automatic large angle tracking. This technique was applied for hadron analysis and also background reduction for opera. And the high automatic recognized efficiency for large angle MIPS is found in our work. And currently, there is many other trial and update for large angle tracking. So after tomorrow, Ariga-san's talk and the Valerie's poster. Okay, then the next session, the high discriminated tracking. So this is I explain the current emulsion analysis in the opera film. First, we scanned the opera film. This is we called fake track, the low energy electron. This is a true track. But after scan, we have many noise chance coincidence of noise track. So after that, we must judge the signal and the noise by eye check, by manually. So we want to reduce eye check process because it's a very heavy work. So this is the motivation for development of high discriminated for the SN tracking. So this is the past progress for high SN tracking. We developed a high discriminated method on basis of log likelihood analysis for CS analysis in opera. So that means that in CS is constructed the 2 opera film, so the 4 emulsion layer. In this time, I talk about this. I don't talk the detail in this method. So if you have an interest after talk, please discuss with me. And the point is we evaluate the this track linearity of data and the blackness of data. So this is a signal and noise. So this area is no eye check. Also this area is no eye check. So automated judgment. But the selection parameter from a normal scan is already finished up. So the tracking algorithm itself should be improved for furthermore SN improvement. So we developed the new tracking algorithm. So the point 1 is increasing image information. Normally we take 16 layer scan. In this time we tried the 32 layer scan. And also the additional judgment for microtrack, the pick up the new selection parameter. So one is the linearity of grain, and the 2 is the number of grain. So around the track. So this is a fake track. This is a true track. And finally, we we took the maximum gap between hitting layer. So this is the Compton and the fog chance coincidence. This is the evaluation of noise reduction rate. Sample. The sample film were exposed beam, and the film were scanned by normal scanning system. So this is the evaluated the log likelihood analysis, the signal and the noise. This area is I check region. This is the sample for this analysis. So the effect of a 32-layer scan. The scanning condition, the brightness filter for binarization and the expansion filter is so changed. We investigate the recognized rate of true track and fake track. In this time, we select the 99% recognized rate for true track. And if request at least one track for 2 layers. In this case, if we reject track which are not recognized on both sides, so the 58% noise track the rejection, but true track is keep the high efficiency. Okay, the next, this is a new parameter, about new parameter. This is the linearity of grain, so true and fake, and the number of grain around the track, true and fake, and the maximum gap between hitting layer is true and track fake. Okay, so new track ranking score is calculated based on the probability density function of a new selection parameter. So this is a true track distribution and fake track distribution in the I check region. So we can reject this region. As a result, the base track which have the fake track, just the new track ranking score were rejected. So the about 50% noise reduction. Okay, so the totally the 32 layer and the new selection parameter I reject the about 80% noise reduction, but the true track were kept on 99% efficiency. So this is the same one, and for opera film, this is the result, and in the case of CS is a opera film doublet. So for true track, the 98% survived, and the fake track rejected 95% additionally. Okay, the summarize. We have been developing high discriminated tracking method. This will allow an automation of a nuclear emulsion analysis. And we also developed a technique for automatic large angle tracking. And this technique was applied for hadron analysis and also background reduction of opera. And also the high automatic recognized efficiency for large angle MIPS is found in our work. Okay, so in this talk, I introduced the pioneer works, which is qualitatively different from conventional development strategy speed up. I hope many kind of improvement for the scanning is done. That's all. Thank you.
Joint discussion or cooperation, for example, with Napoli group is concerned this problem, because very useful for cooperation.
So I continued the discussion the Napoli group and any other group for the.
Your work not closed for
first, this work only me, but now I talk in Opera collaboration meeting, so many people interested some work and start.
I wish to comment that interesting byproduct of your work can be analysis of fragmentation of target nuclei induced by muons and neutrinos. So these histograms were rather small to catch, but it is, of course, multiplicity of black particles is low in your case.
So you mean
Too small. Second chapter, maybe. This one.
this is a
So it's difficult to resolve.
this is a multiplicity.
Yes,
Of,
multiplicity induced by what?
This is the incident momentum of hadron.
Hadron.
Yes, pion.
Interesting to see the same analysis with muons.
Oh, thank you.
Thank you very much again. Well, and we would like to ask next speaker. Mamatkulov research is one implantation of heavy iron in emulsion with energy 1.2 MeV.
So my presentation about implantation of heavy ions, krypton and xenon in emulsion with energy 1.2 MeV per nucleon. So layers of nuclear emulsion was irradiated with ions krypton and xenon with energy 1.2 MeV in session March in this year. At the accelerator complex IC 100 at laboratory flare of nuclear reaction in Dubna. In the slide shows the scheme producing a beam of ions and place for nuclear emulsion layers. Since this energy is since the energy is small, it was necessary to use emulsion layers without protection papers, through which these ions cannot be get into the emulsion. Therefore, we have to close all slits in this room like this with black paper and work under red light as a photo laboratory. And needed track density was about 10.6 ions per centimeter square, and we needed about 5 seconds for radiating, which corresponds to the parameters of accelerator. This is a setting for irradiating the polymer films. This is pull out of the vacuum chamber with the board for mounting samples. Placing detectors like this. Emulsion layers with size 9 to 12 centimeter and with thickness for xenon about 100 micron and for krypton about 180 micron on a glass substrate with thickness about 2 millimeter placed at an angle 45 degree to the beam axis, and tilting plate has provided observability tracks of ions in the emulsion. This is our microscope room. And this is a KSM, which is measured coordinates, length, and side tension. First time when we irradiate with ions krypton, we use 25C series of plates, and we use in vacuum chamber, and when we get it, we find cracked and pieces of glasses, and of course it was not good for accelerator. And when we planning irradiate with ions xenon, we decided to use previously test all of series plate in vacuum chamber, and we get results that, for this series same results, and we see that for xenon it was okay. In the slides you can see examples of microphotographs of tracks krypton with magnification 10, 20, 60, and 90, and entering to emulsion in this picture is from top side. And in this, for xenon, of course, for xenon we previously marked emulsion. In this slide, you can see a screenshot of simulation program SRIM. It means stopping ranges of ions in matter. You can choose isotopes of ions. You can add energy, and you have to add layer or layers if you have many, and just you have to add thickness of layers and run, and you can get ion ranges, ionizations, and ion trajectories. In this slide presented average length of measured 40 beam tracks, and red is a fake length because we get information about previously thickness of emulsion, and these results not was right, and we decided to remeasure thickness of emulsion, and after correction of shrinkage rotate, we get true length of ions, and it was for krypton 14 micron, and for xenon is 17.5 micron, which corresponds to the calculated results from model of SRIM for krypton and for xenon. This difference between experiment and between model lengths can be attributed to this additional breaking of ions on the residual air in installation. In this slide shows the angular distribution of ions for krypton and for xenon. And after correction shrinkage ratio, we get for krypton 43.7 degree. For xenon is 44.7 degree, which corresponds to the oriented angle. In the slide presents an energy distribution of ions, which is obtained on the basis of spline interpolation, calculation range energy by model stream. Their average values after correction on energy, after correction shrinkage ratio, amounted for krypton about 0.7 MeV per nucleon, and for xenon is 0.9 MeV per nucleon. And in this picture, this is a xenon, krypton, and this is a calculation by stream model. And this is our summary. Thank you.
Thank you very much. What about question? Comment? Maybe some remarks. May I ask you why the name of your report is implantation? Maybe more correctly to say irradiation, no?
I think because our irradiation, why not irradiation? Because our ions stopped in emulsion. No, implanted.
No.
They stopped in
No,
emulsion.
no. I believe that we can say about implantation when we go inside gel or emulsion before irradiation and some working. This one mean
It comes from electronics. We make implantation, beam implantation, and docking on the surface. And this stream model is particularly good for solution of electronic problems, like docking of ions of boron to some electronic components.
I understand. You use emulsion like model for future electronic.
No, maybe I can comment on this also. Our motivation to do this study was laser plasma, and energy of ions is about 1 MeV. That is was promised in laser plasma, and the idea was to stop. But after some work, it's become clear that without photo covering, we are not able to do. In laser plasma, I show you photo sample. We see just electrons and electrons penetrating, and ranges of in emulsions of such ions is 14. Maybe next time we shall make more systematic verification of this ring model, how to implant and to stop ions, and to make different implantation angle 10 degrees or something else. So that, it's about laser, very low. Maybe next step of this study can be possible with electron cyclotron ACR source or fluoride test source, which has provides energy of few hundred kiloelectron volts. And interesting to compare dynamics when ion comes. Already this is sure for sure implantation. 100 kiloelectron volts is like electronic.
Okay. Thank you very much, Maria. We finished our morning session. May I ask permission for coffee break?
11:00, perfect.
Possible. Okay, thank you very much. Coffee break.
Like train.
Train in Germany.
Ну что, вы поняли, что мы делаем?
Нет.
Все равно не поняли.
Okay.
Садись, объясняй.